Hi, I'm Professor David Farina. In today's video, we're going to be discussing the Sun, our star, in particular the active Sun. Let's get started. What we mean by active Sun is that it is currently undergoing a period of solar activity, or sunspot cycles. So during a sunspot cycle, the Sun has dark areas, which are called sunspots, which are peppering its surface. These sunspots are going to go through a 11-year-long cycle that is going to have an increasing number and change of location of the sunspots throughout the cycle. Each of these sunspots can be enormous, much larger than the Earth itself, and their temperature is only about 1,000 degrees smaller, or lower I should say, than the surrounding solar surface, but that temperature difference is enough to show up as this dark area. However, each of these sunspots are equivalently as bright as the full moon. So don't be dismayed by their dark appearance. They are extremely bright. What is a sunspot? Well, a sunspot is simply a magnetic field line that's being extended through the sun's photosphere. And while it looks like two separate spots, a sunspot is actually going to be a pair produced by the north and south poles of the magnetic field lines extended through it. So we see here that each sunspot has both a south and a north, and the field lines come out of the south and go into the north. And this is the path by which the material of the sun's surface actually can flow because it is a plasma. Ionized particles are able to flow through magnetic fields, and so the sun's actual physical material is being pulled up and through, and it makes this very cool, almost Berber carpet-like look on the surface. Now, sunspot cycles are caused by the rotation of the sun and the fact that the sun is made of a material that is not solid. So, in other words, over time, we start off our sunspot cycle. In our lab, we talk a little bit about this in terms of like a rubber band. And then we start to twist the sun, and you'll notice that towards the poles, the sun does not rotate as fast as it does along the equatorial regions, and so they start to get stretched and warped more and more and more over time. And as they start to cause kinks, those kinks are represented as places where those magnetic field lines are extended through the solar photosphere, and we see them as a sunspot. Sunspot cycles happen over, as I said, about an 11-year-long cycle, and they start off at latitudes of 30 north and about 30 south, and then they migrate slowly over the course of the solar cycle, that 11-year-long cycle, towards the equator, at which point the cycle stops, and the poles reverse. And then we end up with a second sunspot cycle, and find my mouse, there it is, where once again it starts off at 30 north and 30 south, but the main difference here is that the north and south pole of the sun actually do a flip each of these times. So every 2 cycles, so let's say this was north and this one was south, in the next cycle this would be south and then this would be north. And then we would start our magnetic cycle over again, north and south, south and north. So there are 2 cycles that are piggybacked on top of one another. For every 2 sunspot cycles at 11 years each, we have a 22-year-long magnetic cycle. As you can see, sunspots are peaking when we're at about the midway point here. And once again, sunspot cycle at the midway point. Now, right in this portion of the graph in current times, you're seeing that we're leading off towards the end of a solar cycle, and then starting in approximately the 2020 time period or so, we're going to start our next solar cycle. So about every 5.5 years you get a maximum, and then it trails back off towards a minimum again. Now, the Maunder minimum is a very important time period, and it's associated with something called the Little Ice Age. During this time, the Little Ice Age, the Earth actually got a lot cooler than it normally would, and this is we believe, as a result of solar activity. So this is one way in which the sun actually can affect climate. Now you'll say, well, is this something that could play a role in climate change? Please be aware, we are understanding that the solar cycle does play a role in climate and does not appear to be causing any changes in modern climate. So we are keeping this in terms of our variables in our bag of tricks when we consider how climate change on Earth is affected. Now, in the past, the Maunder Minimum and the Little Ice Age did have a lack of solar activity, which resulted in a cooler Earth. So that would indicate that a higher amount of solar activity, more magnetic field, equals a warmer Earth. So they're still trying to figure out the link between these, but the thought process is that when the sun has a weak magnetic field, it allows in more cosmic rays, which produce more clouds on Earth, and those clouds on Earth result in a shielding of the sun and its rays from Earth, cooling it. So there's a very interesting correlation here that we're still trying to understand. Areas around sunspots are very active, and as we've discussed in previous videos, these loops here are caused by the magnetic fields extending out from the sun towards, from the south towards the North Pole of the magnetic field lines, and as those magnetic field lines are coming out of the surface, charged particles, or plasma, which the sun is made of, are able to flow along those paths. A solar flare is caused when a large explosion of the sun's surface emits a large amount of energy, and it's very similar to a prominence. So a flare here on the surface can release energy in great amounts in very, very short periods of time. A coronal mass ejection is something on a great scale. So a coronal mass ejection is extremely larger than the Earth, and as it is coronal material, it's ejected, as its name implies, and if those coronal mass ejections are pointed towards the Earth, it can interfere with Earth's magnetic field. We would see a spectacular aurora, but we could also potentially be at risk of damaging our very, very technologically advanced society. And things like power lines could bring in energy from effectively the sun, causing it to fry your electronics. Our satellites are at risk as well, so things like GPS are of major concern, especially to the military. So this is a national security issue, and therefore the sun is extremely, extremely closely monitored by our government. The solar wind, of course, is particles that are released from the sun at all times, and the solar wind generally escapes through something called a coronal hole, which can be seen in an X-ray image. So coronal holes show up here as dark, and these coronal holes is where it allows the sun's wind to be propagating from. And here it kind of shows you where the field lines are from the sun's magnetic field are extended out into space, and this is where we get the solar wind from. The corona of the sun also changes during the sunspot cycle, and as a result, during a solar maximum, the sun's corona would appear larger and possibly more irregular as sunspots peak. So thanks a lot for watching today's video on the sun, our star, in particular the active sun. If you like this video, please click the like button. If you'd like to learn more, please subscribe. And if you'd like to get a notification each time I make a video, please click that bell at the bottom. Thanks again, and have a great rest of your day.